Okay, we're moving into a new topic, area and definite integrals. So, to get started, we're going to look at a very important theorem of calculus. It's called the fundamental theorem of calculus. And it starts with if a continuous function f. So first off, f has to be continuous. Got it? No breaks in it, no open holes, a continuous function. And it has an antiderivative, we'll call it capital F, over an interval AB. Notice the interval is closed, it has brackets. So if you've got this continuous function little f and it actually has an antiderivative capital F over that interval, then here is the result. So some of you may remember this notation. It's sigma. It means summation. So we're summing from 1 to n f of x sub I. So plug in 1, x sub 1 to f. Get an answer. Multiply it by the change in x. That's normally the width. Plug in I equals 2 to f. Multiply it by the change in x. Again, the width. Here's the deal. This part I don't want you to be so concerned about right at this particular point in time. It's not as important for business calc majors as it is for the engineer majors, the pure math majors, that type of thing. Y'all with me on that? All we need to really know right now is that the limit of this summation is actually equal to the antiderivative of the function over that interval. Now, based upon the way this interval is written, A is the smaller number, B is the larger number. Got it? And normally when we take the antiderivative, we add a C, don't we? Well, because we actually have numbers here, we actually have an interval to work off of, C doesn't come into play anymore. We actually will take the antiderivative and evaluate it at the larger number, take the antiderivative, evaluate it at the smaller number, and then subtract larger from smaller. With me? Okay. Now, here's the deal. This part is extremely important for us at this point in time. This antiderivative and this evaluation comes from the limit of the sum. This antiderivative evaluated over an interval, a certain interval, actually helps us to find the area of a graph. So let me give you a for instance, a very simple for instance. They're asking us to find the area under the given curve over the indicated interval. Well, as I mentioned, this helps me to find the area. So my function is y equals 4. To find the area using this antiderivative, we are going to be taking the antiderivative of 4 with respect to x, because normally when we graph we have an x and a y. And now they have it over a certain interval, 1 to 3. 1 being smaller goes at the bottom of the integral sign. 3 being larger goes at the top of the integral sign. Now, you know how to take the antiderivative as well as I do. And by the way, I'm just going to say A of x, A standing for the area. So the antiderivative of a constant is just going to be, in this case, 4x. Now, normally we put a C plus C, correct? But because I actually have a certain interval to work off of, I am going to take this antiderivative and I'm going to evaluate it from 1 to 3, from the smaller to the larger. Based upon our theorem, once we have the antiderivative, I'm going to take the top number, the larger number, and plug it in. So I'm going to do 4 times 3, and then I'm going to subtract, and then I'm going to take the smaller number and plug it in, 4 times 1. And when I do my arithmetic, I am going to get 8. So what this is telling me is the area under the curve is going to be 8 units squared. Now, let me show you this graphically. Because you're like, okay, I get how to take the antiderivative, but I don't see how it's relating. Let me show you this graphically speaking. I'm only dealing from 1 to 3 on the x's. So I'm just going to draw quadrant 1. So from 1 to 3. Y equals 4 is a horizontal line crossing the y-axis at 4. Yes? Okay. So, y equals 4. And now the question was to find the area under this given curve. Well, over the interval. Well, the interval is going from 1 to 3. And I'm trying to find this area under the function they gave me of y equals 4. Now, if I notice, based upon this graph, from 1 to 3, and then under y equals 4 basically creates a box, right? Well, I shouldn't say a box. It creates a rectangle, correct? Okay. Now, answer me this. How do you find the area of a rectangle? Yeah, length times width. So if I just look at this rectangle and I look at the length and the width, the length from 1 to 3 is 2. Now this width, yeah, it's 4 units high, isn't it? Which means if I find the area, I'm going to do 2 times 4, which means the area is 8. Great, I got the same answer when I took the integral. When I took the antiderivative of y equals 4, I got the exact same answer, didn't I? And some of you may be like, well, why didn't we just graph it in the first place? That was easy. You're right. That one was easy. But you know as well as I do, we're not always going to be given nice, simple, easy functions to find the area under. We could be given these third-degree functions to find the area, and you're like, oh my gosh, how do I do with all these curves and et cetera, et cetera? Yeah, that's where this fundamental theorem of calculus comes in extremely handy. Because when I take the antiderivative and evaluate it at the higher and lower number and then subtract, that's just as good at giving me the area as graphing it. Got it? Okay, got another example for us. Let's look at the second example. Directions are the same, find the area under the curve. Now, we could graph that on this interval and then look at the area under the curve and try to find it. And some of you are like, that doesn't sound too fun. Let me just draw you a quick graph. I'm looking from 0 to 5. So I'm just going to draw axis 1, or pardon me, quadrant 1. Okay. And we know that's a parabola, right? So 0, 0, 1, 1, 2, 4, it's going to do something like this. And if it wants the area under the curve, that means we are looking for this area. Now, you can try to figure that out manually, and there is a way to do that. It's called Riemann sums, which is where the first part of that fundamental theorem of calculus actually comes from. Or you can look to see if this is a continuous function, which it is. Would it have an antiderivative? It would. We're familiar enough with that. That being the case, I could actually just take the antiderivative of that, evaluate it over the interval 0 to 5, and I would come up with the area under the curve. Sounds a little bit simpler, doesn't it, than trying to figure out the area based upon this graph, right? Okay, so based upon the theorem, to find the area under that graph, we're going to take the integral from 0 to 5. Remember, 0 being the smaller number goes at the bottom of the integral sign. 5 being the larger number is it goes at the top. And I'm going to take the integral of x squared with respect to x. Good? Okay, so you know what the antiderivative is of x squared as well as I do. What is it? Yeah, it's 1/3 x cubed. Now, normally we add the plus c, don't we? However, because I have an interval from 0 to 5, we're going to evaluate it from 0 to 5. So, according to the theorem, we are going to take 1/3 multiplied by 5 cubed after I plug the 5 in, minus 1/3 times 0 cubed. So it basically looks like 1/3 times 125, because the other one cancels out, it's just 0. And unless it asks for a decimal, don't give it a decimal. We end up with 125 over 3, which is 41 2/3 as a mixed number. And this would be the area under the curve. So if you look at this drawing, it would be 4 2/3 as its area, units squared, whatever it is. Good? Okay. Number 3. Now, you could draw the graph of that and try to do it by hand like I showed you on number 2. That's what the graph of x squared looks like from 0 to 5, and the shading is under the x squared graph. Or you can take the antiderivative. You can use the fundamental theorem of calculus, which I think will be a little bit easier to do. Don't you agree? So gratefully, that's a continuous function. It's going to have an antiderivative because we're looking at it and our brains are already thinking of an antiderivative, and we should be able to evaluate it from -1 to +1. Good? Okay, so let's check it out. Our area then is going to be the integral from -1 to +1. Remember, smaller number at the bottom of the integral sign, larger number at the top of the integral sign, of 1 minus x squared dx. Okay, you know what the antiderivative is of 1 minus x squared as well as I do. What are you getting? Yeah, x minus 1/3 x cubed. Agreed? Now, you going to add a plus c? No, you're right. I don't need to add the plus c because I'm going to take this antiderivative and evaluate it from a -1 to a +1 because that was the interval I was working off of. By the way, that interval is a closed interval, correct? Which is what the fundamental theorem of calculus says. So is number 2. We forgot to check that, sorry. All right, time to start plugging these numbers in. So our area, when we plug in a +1, we're going to have 1 minus 1/3, aren't we? Okay, and I'm going to subtract that, and now I'm going to plug in the -1, which is going to be -1 minus, yeah, -1/3, isn't it? Because when you plug in the -1 and cube it, it's still negative, isn't it? Which makes this a +1/3. Agreed? So, you've got what? A -2/3 minus, looks like a +2/3, which gives you -4/3, right? Okay, which would give you, I'm sorry, that was a +2/3 minus a -2/3. See, this is why I need you guys doing it with me. I heard you. My fault. This was a +2/3 minus a -2/3, which makes it a +4/3, and that's 1 1/3 if they want a mixed number. By the way, if I get a negative area, something's wrong because area is not negative, is it? Yeah, that right there was kind of like our tip-off, like something's wrong here. Anyway, so far so good? Loving it. Got another one. Let's look at this third problem. The function is x cubed minus 3x, and they want me to find the area from a -1 to a +1. So this function is continuous. My interval has closed brackets, so we're good. Over here, I actually drew it so you could see what it looks like. The graph is this third-degree polynomial that looks like that. And when you're trying to find the area they're actually talking about is between the graph and the x-axis. So on the 0 to -1, the area between the x-axis and the graph, notice it's above the x-axis, right? Whereas when you look from 0 to positive 1, the area under the graph is actually the x-axis to the graph, which is below the x-axis. That's why the shading looks like it does. Good? Now that would be very interesting to find the area of that graph by hand. Gratefully, we don't have to. We can use fundamental theorem of calculus. So to find this area, we are going to take the integral from a -1 to a +1 of x cubed minus 3x with respect to x. Good? Okay, you know what this is going to be as well as I do. We're going to get 1/4 x to the 4th minus 3 times 1/2 x squared. And that whole thing, so I'm going to put it in brackets just so it's easier. You could put it in parentheses. You're going to evaluate this whole thing from -1 to +1. I'm going to simplify the function inside the brackets a little bit so it's easier. So I get 1/4 x to the 4th minus 3 over 2 x squared. And we're going to evaluate that function from a -1 to a +1. With me? All right, so here we go. The area is going to look like, we're going to plug in the +1 first, so we get 1/4 minus 3/2. And then we're going to subtract. All right, plug in the -1. -1 to an even power is going to still be a +1, correct? Which means in the other bracket, I get 1/4 minus 3/2 also, don't I? All right, so we could work these out. We can get a common denominator, which would be 4. So the 3/2 changes to a 6/4. Agreed? And then I'm going to continue it over here. The area under this is looking like, in the first bracket, we get a -5/4 minus, in the second bracket, we get a -5/4, which means what? We get -5/4 plus 5/4, which means the area under the graph is actually a 0, isn't it? Well, that's interesting. You're like, why is it 0? That doesn't make sense. It actually does make sense when you look at the graph. So remember the graph I drew in the beginning? Do you notice from 0 to -1, I have the graph above the x-axis? Do you notice from 0 to +1, the graph is below the x-axis? What this tells me is the amount of the graph above the x-axis and the amount of the graph below the x-axis is exactly the same. So they canceled each other out, which is why I actually have an area of 0. That's why I drew the graph here, because it's visually easier to understand why you have a 0 by looking at the graph. Good? Loving it. Got some more examples, so stay tuned. All right. Back with another example. This one simply asks us to evaluate. Now remember the title of this particular lecture video? It said the area and definite integrals. We have been dealing with definite integrals up until this point. When they gave me the interval to work off of, notice I had put those numbers at the bottom and the top of the integral sign. That made it a definite integral, which means I didn't have to have a plus c. Well, this example that I've given you, they've already given you numbers at the bottom and the top of the integral sign. It says the integral from 1 to 5 of 2x squared plus 7 dx. This is a definite integral, just like we've been working with all those area problems. I don't have to have a plus c. because it gave me numbers to evaluate the antiderivative at. Good? Okay, so time to take the antiderivative of this particular function, 2x squared plus 7. All right, so you all know how to do this as well as I do. Since there's the addition sign, you look at it separately, right? So I've got the 2, and what's the antiderivative of x squared? Good, 1/3 x cubed. And what's the antiderivative of 7? Good, 7x. And, yeah, no plus c, because you're going to evaluate this from a 1 to a 5. Now, I am going to put brackets or parentheses, whatever you prefer, around the antiderivative that I have so far. So I'm going to simplify inside there. So I end up with 2/3 x cubed plus 7x. And I'm going to take that antiderivative and evaluate it from 1 to 5. So, what are you going to do first? You're going to plug the 5 in first. So let's plug the 5 in first. We're going to have 2/3 times 5 cubed plus 7 times the 5, right? Okay. And then I am going to subtract from it 2/3 times the 1 cubed plus 7 times 1. Got it. All right. Now I know some of you are on your calculators already. Well, I'm just going to do some work by hand here. We're going to have 2/3 times the 125 plus 35 in that first parenthesis. And then I'm going to subtract from it 2/3 plus 7. Got it. Well, unfortunately, 2/3 times 125, nothing's going to cancel there. So it looks like I have 250 over 3 plus 35 minus 2/3 minus 7. Right? Because I distributed that minus sign in between, didn't I? Now, here's the cool part. I'm going to subtract things that are the same, combine things that are the same. So I'm going to take 250 over 3 and minus the 2/3. What are you going to get? Yeah, we get 248 over 3. And then I'm going to take the 35 and minus the 7. Yeah, gives me a 28, doesn't it? Right? Okay. At this point, I am going to take 248 over 3, and I'm going to make the 28 with a denominator of 3. Makes it a little bit easier. I know you guys are on your calculators, and that's fine. So I get 84 over 3, and then I can add them together. And then, if they like, unfortunately, 332 over 3 doesn't reduce. If they like, I can make it into a mixed number. So I would get 110 and 2/3 as my answer. Good? Here's the deal. You kind of need to know how to work with this stuff using your algebra skills. Notice what I did. As opposed to making all 4 of these numbers with a denominator of 3, I just combined those that were the same. The 250 over 3 and the negative 2/3. That's how I got 248 over 3. And then I took a plus 35 minus 7 and got the 28. And then all I needed to get is change one fraction, 84/3. 28 turned into 84/3. I could add them together, get my mixed number, and I was good to go. Right? Awesome. Got another one. All right, let's look at the second problem they're asking us to evaluate. They're asking us to evaluate from 1 to e to the 4th of the function 4x plus 6 over x with respect to x. That's why the dx is there. So, yeah, gratefully there's an addition sign between the 4x and the 6 over x. So we can look at them separately, can't we? Now, in this particular case, I'm actually going to look at them separately, and I'll show you why. We are going to take the definite integral from 1 to e to the 4th of 4x dx. And then we're going to add to it the definite integral from 1 to e to the 4th of 6 over x dx. Agreed? Now, I can take this 4 on the outside. So 4 times the definite integral of 1 to e to the 4th of x dx. And on this second integral, I can take the 6 out. 1 e to the 4th, 1, 2 e to the 4th of 1 over x dx. Agreed? Okay. And now, let's look at taking those antiderivatives. Now that I've got the constants out, actually now that I split them apart first and I took those coefficients out, let's see what this looks like. So we're going to have 4, and we're going to multiply it by the antiderivative of x, which would be 1/2 x squared. And then we would take this and we would evaluate it from 1 to e to the 4th, wouldn't we? Plus 6. Now what's the antiderivative of 1 over x? Come on, let's see if you remember it. Yeah, good job. ln of the absolute value of x. And you're going to take that and evaluate it from 1 to e to the 4th. So I can actually make it into 2 separate problems like you see here and then recombine the answers. So let's work this out. Let's keep going. So 4 times 1/2. Good. So I have 2x squared. That I shall evaluate from 1 to e to the 4th. And then 6, natural log of the absolute value of x from 1 to e to the 4th, evaluated. All right, time to start plugging numbers in, agreed? I am going to go to the top over here of this other side of my board because I have more room. So, you're plugging in e to the 4th to 2x squared. So 2 e to the 4th being squared minus 2 times the 1 being squared plus 6 ln of e to the 4th minus 6 times ln of 0. So far so good. All we're doing is plugging numbers in. All right. So 2 times e to the 4th is being squared. What would you get? E to the power of 8. Great. 2 times 1 squared. Yeah, minus 2. Okay. And then we're adding to it. Okay. 6 times. So I'm just writing the 6 for now. So what I need to remember is what the natural log of e to the 4th is going to be. Yeah, some of you remember, some of you don't. Remember, natural log is log base e, isn't it? And you're taking the log base e of an exponential function that has a base e. What are they going to do? Since they have the same bases, they're going to cancel out, aren't they? So log base e of e to the 4th, yep, that's going to be just a 4 because they cancel out. Log base e and e to the power, those are going to cancel, which leaves me just the 4. Minus 6 times, and now you have to remember what the natural log of 0 is. Or log base 10 of 0, or log base 5 of 0, or log base 11/3 of 0. Yeah, that's always a 1. Got it? Okay. And now, actually, I'm sorry. I knew that sounded funny to me. Over the line above it. And some of you were saying, wait a minute, that's not right. Yeah, I heard you finally, because I saw my mistake. I'm taking, on this line, I erased the natural log of 0. I'm actually taking the natural log of 1, aren't I? So the natural log of 1 is 0. And you're like, well, wait, why couldn't you be a 0? Why can't you take the natural log of 0? You got to remember the domain of a log function. I don't care what the base is. The domain is 0 to infinity, not including 0. So that should have been my tip-off when I put a 0 in there, but I wrote the wrong number. See? My brain was thinking ahead. Sorry. Okay, but let's keep going. So we have 2 times e to the 8th minus 2 plus 24 minus 0, which gives me 2 e to the 8th plus 22. Agreed? Okay, I am agreeing. Sorry, just looking real quick. Yep, I'm agreeing. All right. Agreed? Cool. I have some stories coming up next.